Good afternoon, everyone. Can you hear me all right? Nobody responded. Ferris, can you hear me?
Oh, yeah, I can hear you.
Okay, good. I'm going to take it that everyone else can hear me too then. Good. Plan today is to cover section 7.4 and 7.5. And before we start that, I'll take any questions you might have on 7.1 and 2, if there are any homework or any issues you had on those. Everybody get through 7.1, 7.2 okay? You guys are good. I'm going to take that as yes, you got through it okay. All right. Very good. Let's go on to today's material then. 7475. 74 talks about systems of nonlinear equations. Last time we covered them, we were looking at systems of linear equations. These are going to be nonlinear. They might be circles, they might be parabolas, or who knows what shape they might be, but they're nonlinear. And we're going to look at two variables. Later on, we might look at more variables than just two, but we're just going to look at systems of nonlinear equations, two variables. Objectives, we want to be able to recognize them. We want to see if how we can solve them. Can we solve them by substitution or addition, sometimes called elimination? And then maybe take a look at some problems that we can solve. And feel free to be sure you ask questions as we go through the material. So let's go ahead and start. And let's say I give you the following nonlinear equation. Maybe it looks like x squared equals y minus 1. And that's the first equation. And the second equation might be 4x minus y equals -1. And I might say, can you solve by using the substitution method? Okay, now there's more than one way we could solve any of these problems we're going to go through. I'm going to take you through a method, but you certainly could use a different method if that works better for you. So what I'm going to do is put these maybe in a different form. Maybe I'll say solve this first equation for y. Looks like it might be fairly easy to solve. So I could say y equals x squared, add 1 to each side, x squared plus 1. So this equation now looks like this. So that was what I always do when I'm going through these, is just try and pick whatever is the easiest method to solve it. So it looks like if we're going to solve by substitution, that would be easy. We could have solved this one for y as well. So now that we have y equals x squared plus 1, we can substitute that into the second equation. So the second equation becomes 4x minus y, and y we've solved as x squared plus 1. So it's negative, this binomial quantity here equals -1. So we did the substitution. Now we want to take this negative and distribute it through the binomial. 4x minus x squared minus 1 equals -1. And then solve, and I've got a -1 here and a -1 here. Looks like those are going to cancel. And then I can say, well, I've got an x and an x squared. Looks like I could factor out an x and make that 4 minus x equals 0. X times 4 is 4x, X times negative x is negative x squared, so that works fine. And then solving, we can say x equals 0 or 4 minus x equals 0 or x equals 4 in this case. So we've got two situations then. If x is equal to 0, we want to solve for y. And if x equals 4, we want to solve for y. So let's go ahead and put that in the above equation. Let's say x squared equals y minus 1. If x equals 0, y minus 1, or y equals 1. So our solution set for one case would be x is 0, y is 1. That's a solution. And over here, we had x is 4. So we could say x, well, let me just maybe just make it simpler here and just say 4 squared. 4 squared equals y minus 1. So 16 plus 1 equals y, which is going to be 17, isn't it? So when x is 4, y is 17. So here's our two situations. So we can say then our solution set is 0 and 1 and 4 and 17. And we'll put the solution set inside these braces here and say, there's our answer. So we started out with a couple of equations. We were given the method to solve it by. We went through our solution technique, solve for x, could have solved for y, and then substitute back in. Okay. I'm going to stop at that point. Before I check my answer, I'm going to stop at that point and answer any questions you might have.
Could you explain the process after like x equals 0 and x equals 4? Could you explain like what you did after that?
Right here?
Yeah, everything else below, like
Yeah.
x equals 0 and x minus equals 4.
Right. So here are my original equations. And now I have solved for the x value. So I started out with an equation that said x squared equals y minus 1, and I've solved for x. So if x equals, what did I say? Well, 0 in one case. So if x is 0, I put 0 squared equals y minus 1, or y equals 1. So when x is 0, y is 1. And we said that's one of the solutions. It makes sense?
Yeah.
Okay. And then we did the same thing for y is 4, or x is 4. We said, well, x squared equals y minus 1. If x is 4, that's 4 squared equals y minus 1. 4 squared is 16 equals y minus 1. Add 1 to each side, and we get y equals 17. That's what we got here. And we said that's another solution set. So we've got 0 and 1 for x and x and y could be 4 and 17. Now we could be asked to check our solutions. So we just plug those back in. We had x squared equals y minus 1, and we had 4x minus y equals negative 1. And at 0 and 1, so if x is 0 equals y is 1 minus 1, which is 0. So 0 equals 0. That's true, isn't it? So that solution checks. We could put another solution might be 4 and 17. So we have 4 squared equals y, which was 17 minus 1. 4 squared is 16. 17 minus 1 is 16. So that's also true. So these solutions check for the equation. Okay, questions on that at all? We could also do the same thing on the right-hand side over here. Okay, everybody okay? Okay, let's take a look at another problem. Let's say I've got x plus 2y is 0, and maybe the quantity x minus 1 squared plus the quantity y minus 1 squared equals 5. See if that's something we can solve. So if we were to do that, we're going to end up taking these values here and seeing what they're equal. So if we square x minus 1, what are we going to get? X squared minus 2x plus 1. Is that what we're going to get? Plus y squared minus 2y plus 1 equals 5. Okay. So if we were to solve by substitution, well, it looks like it would be easy to substitute for x, wouldn't it? We could easily solve for that. So I could say, first of all, I'm going to say how we're going to solve this. Now, you might be given these problems and not told a method to use to solve it. You might say, hey, given all the methods that you've learned, go ahead and solve this system of equations. But we're just taking you through step by step here. So if I say solve by substituting for x, solve that for x, I could say x equals negative 2y, couldn't I? So I guess I could put that in here, make it easier. Negative 2y minus 1 quantity square plus y minus 1 quantity square equals 5. So here I started off by saying, well, let me just do all this and expand all this, but maybe that's not the thing we should be doing. Maybe we should be stepping back and saying, if I'm going to solve this, and I've told to solve it by substitution, let's either solve for x or solve for y and substitute back in. Solving for x seems to be fairly straightforward because we can just move y to the other side and get this value here. Then we can just substitute that in. So I get negative y quantity, negative y minus 1 quantity squared for this value here, and then y minus 1 quantity square for the second equation. So I've started off with two equations, solve the first equation for x, and then substitute into the second equation. And then when I expand that, let's see, negative 2y, so that's positive 4y squared, negative 2y minus 1. So if I do a FOIL, first times first, positive, outer, so I get negative times negative 2, so that's positive 2, and here's the same thing, so that's going to give me a positive 4y, isn't it? Outer and inner when I combine those. And then when I multiply last times last, I'm going to get a positive 1. Okay. Plus the second value squared here, this binomial, which is going to give me, if I FOIL this, y minus 1 first times first is y squared minus 2y plus 1, isn't it? Equals 5. So everybody agree on where we are given these two equations? Solve by substitution, substitute it in, end up with this guy here. Now we want to simplify. So let's combine like terms. So we've got 4 of the y squareds and 1 more. So we have a total of 5 of the y squareds. And for the y's, I've got 4 here minus 2. So that gives me a positive 2y. And for the constants, I have a 1. And what else do I have? Just a 1. So that's 2 plus 2 equals 5. Well, this is starting to look like something we could simplify, set it equal to 0. So I can bring this 5 to the other side, subtract 5 from each side, and I'll get 5y squared plus 2y minus 3 equals 0. Okay, everybody agree so far? Okay, so now we want to factor this thing. Because the object of this game is to solve. So we look at the factors of the first term here. Well, it could be 1 and 5 or 5 and 1. And this one could be 1 and 3 or 1 and 3 that way. Okay, so we'll see if we can factor that. Now we want to do outer plus inner and get a 2. So this says that the signs are opposite, and this says that the larger one is positive. So if I say 5y and y and 3 and 1, using this and this, the signs are opposite and the larger is positive. Well, the larger one, I FOIL this thing. Outer is 5, inner is 3. So it looks like I want that to be positive and that to be negative based on what I see here. So if I FOIL this, 5y times y is 5y squared. Last would be negative 3, outer 5y, inner negative 3. That gives me that. So that looks like that factors nicely. So then if we set those equal to 0, each one of those equal to 0, 5y minus 3 equals 0, y plus 1 equals 0, y equals 3 over 5, and y equals negative 1. So we've got 2 values for y. Now we have to do like we did earlier, don't we? We have to determine what the x values are going to be. And up above for our first equation, we had x plus 2y equals 0. So if we want to solve for x plus 2 times 3 over 5 equals 0, x equals negative 6 over 5, doesn't it? To multiply this times this is 6 over 5, bring it to the other side. So it looks like I have one solution set that is negative 6 over 5 and 3 over 5. That's one solution. And then over here, y is negative 1. So I should be able to do the same thing. So if I say x plus 2y equals 0, x plus 2 times negative 1 equals 0, x equals 2. So we have a solution set of 2 and negative 1 on the right-hand side. So listing all of our solution sets, then we say in our solution set braces, we'd say we have a solution of negative 6 over 5 and 3 over 5. And we have a solution set of 2 and negative 1. And we would show that as our answer. We always want to box our answer and show me where the answer is by pointing to it. And then all this up here is going to be your work, isn't it? Okay, questions on what we did there? That makes sense to everybody?
Could you show another problem like this?
This is a second problem. we've done 2 like this now so far. I can go through more problems, but solving equations using the substitution method, we did that here. And then we came back and did another problem using the substitution method, which is here. So we've done 2. I'll take you through more problems, but we've done 2 very similar problems using substitution to solve. Now I'm going to take you through an example where we are going to use, you might call it either addition or elimination, where we're eliminating one of the variables. So I might say, given 2 equations, 3x squared plus 2y squared is 35, for instance, and 4x squared, so equation 2 plus 3y squared equals 48. And we can manipulate these 2 equations to eliminate either the x or the y, whatever we think is easier. And it looks like to me, because these values are smaller, the 2 and 3 are smaller than the 3 and the 4, I'm going to use that one. So I'm going to multiply the first equation by, let's say, by 3, and the second equation by 2. So I'm going to create equations 3 and 4 by operating on this equation. So if I multiply it by 3, 3 times 3 gives me 9x squared plus 3 times 2 is 6. Y squared equals 3 times 35. 35 times 35 is 70, and 35 looks like that's 105. And multiplying this by 2, I get 8x squared plus 6y squared equals 48. 48 looks like that's going to be 96. And the idea was I wanted to get the values for y, the amount the same, so that I could eliminate it. So I could subtract this equation from the first equation. So I'm going to subtract. So I'll change my signs here, indicating I'm subtracting. And when I do that, 9 minus 8, so that leaves me an x squared. The 6 y's cancel, and that's going to equal 105 minus 96. 105 minus 96 looks like that's 9. So then I can take the root of each side and say then that x can equal a plus or a minus 3. Okay, so I'll do my situation like I did before. If x equals 3, I want to solve for y. So putting that into the first equation, I could say 3 times x squared, which is 3 squared, plus 2y squared equals 35. 3 times 3 is 9, times 3 is 27, plus 2y squared is 35. 2y squared is 35 minus 27, and we're going to end up dividing that by 2, aren't we? Whatever that comes out to be. So let's see. 35 minus 27 divided by 2 gives me a 4. That's numerator is 8, denominator is 2, so it gives me a 4. So y equals plus or minus 2, doesn't it? Okay. So if x is 3, positive 3, then x can be plus or minus 2. So I have a solution set that looks like x is 3, y is 2, and x is 3 and y is negative 2. That's on one side over here. Now we have to go back and solve for the negative 3, don't we? Here we have a positive 3 for x. Okay, so now we want to do the same thing for negative 3. So if x equals negative 3, what do we get? So 3 times negative 3 squared plus 2 times y squared equals 35. Negative 3 squared is 9, that's 27, plus y squared equals 35. And this looks very similar, doesn't it? 35 minus 27, that should be a 2 there. Over 2, so y squared equals 4, or y equals plus or minus 2 again, doesn't it? So when x is negative 3, y is equal to plus or minus 2. So I have another solution set that says negative 3 plus 2 and negative 3 minus 2. And you could line these up if you want in any order you want. But as long as I say my solution set contains 3 and 2, and 3 and negative 2, and negative 3 and 2, and negative 3 and negative 2. And that's my solution set that I've come up with. And again, I solve this by using the addition, sometimes called elimination method, by manipulating these equations by multiplying through so that I can eliminate a variable. I chose to eliminate y. I could have chose x, but I chose y. Seemed a little simpler. Get questions on that one?
Could you explain the x cubed and x squared part again, like higher up?
The x cubed,
Yeah, you put x3, put x2, like up ahead. It's higher up.
this one, this side or this side?
I know it's a bit higher up. It's like towards the beginning.
Up here?
A little bit higher, Professor.
Up here?
To the right, next to like rows 1 and 2. Like how you do
Oh,
that?
I just multiplied. That's what I'm doing so that I can eliminate, I want to eliminate a variable. So if I multiply this y by 3, I get 6y squared, and this by 2, I also get 6y squared.
Professor.
Yep.
It might help if you just didn't in that parenthesis where the X is at. If you don't put the X there, it will help with confusion for some people, I'm sure.
Okay.
That's all I'm saying. Is just I would just
Yeah.
do the 3 and the 2 in parentheses. And I
Well,
think
I'm multiplying. This says I'm multiplying by 3.
I know, but it's getting confused with the variable, and that's what
All right. So multiply, multiply by 3.
I'm just saying it would.
Yeah. If you're listening to me, I think you'll understand. Make sure you guys follow what I'm doing and question it while I'm doing it. This, remember I said multiply by 2, I can write it out. It just takes a lot longer to write it out. Multiply by 2 or multiply by 2, whatever way you want to do it. So when we're going through these, keep in mind that we're trying to eliminate a variable, whether we're eliminating x or y. Here I multiplied by 3, here I multiplied by 2. So I had the same value for y, the multiplier for y. Then when I combine those, as you can see here, they're both 6. Okay. Make sense?
Yeah, it does now. Thank you.
Okay. All right. All right, let's try another one. Let's see what would be a good example to use here. Well, let's try a little different one just to see if we can. If I give you a triangle and I say we have a length L and a width W, and I say the perimeter of the triangle is 20, let's say feet. And I say the area is 21 square feet.
For continuity, Professor, are we talking about a triangle or a rectangle? Because you've drawn a rectangle.
What did I say?
You said
Yes.
triangle, but you
Oh, did I say triangle? No, that's a rectangle, isn't it?
just making sure.
Yeah, yeah.
Thank
So
you.
if we have this rectangle that looks like this, a length and a width, and we're given the perimeter and the area, and we're asked to see if we can find what the length and width might be. So we look at this and say, well, let's see, the perimeter is going to be this length plus this width plus this length plus this width, isn't it? So that's going to be 2 lengths and 2 widths. And the area is going to, it's 21, and that's going to be a length times a width, isn't it? Okay, so length times width is 21. So it looks like then if I have 2 lengths, 2 widths is 20, and length times width is 21, I've got 2 unknowns, L and W, and I've got 2 equations. So with 2 equations and 2 unknowns, I should be able to solve for that, shouldn't I? Is that something you guys can solve for? Could you solve these 2 equations? Because sometimes setting up the problem is the most difficult part. All right. So if we solve, for instance, if we solve this equation for W, let's say, W equals 21 over L, and then substitute that back in, would that work?
Yes.
Okay, let's give it a try. Now, I'm also going to mention to everybody, let's get everybody involved. We don't want 1 or 2 people dominating the conversation. I would like everybody to get involved. Okay. So I can call on people if people are shy, but I don't want just 1 or 2 people answering all the questions. We want everybody to get involved. If we were sitting in a classroom, I could walk around and pick people. You know, I can kind of see who knows what's going on, who doesn't, and maybe help out. But this way, I'm just going by names that I see on the screen here. So let's go ahead and continue with this. So if I say width is 21 over L and substitute that back and say, well, 20 equals 2, and in place of width, I could put 2 times 21 over L. Wouldn't that work? So now I've got 1 equation and 1 unknown. But I've got something in the denominator here that's an L, which I need to take care of, don't I? So any suggestions on what I should do to fix that so that I can get this out of the denominator? $20 equals 2L plus 2 times 21, that's 42 over L. Well, it looks like if I multiplied through by L, I could get out of the denominator, couldn't I? So multiply, I'll spell it out, by L. So we'll multiply this by L, we'll multiply this by L, and we'll multiply this by L. This will happen to cancel, which gets it out of the denominator. So now I have 20L equals 2L times L is L squared plus 42. Okay, now it looks like we're starting to get into something that maybe we could solve, and it looks like we could also simplify. These are all even values. I guess I could divide each by 2, couldn't I? And I could say 10L equals L squared plus 21. And bringing all the values to the right-hand side, I could say L squared minus 10L. Make that look a little more like an L here. Plus 21 equals 0. Okay. So I've got, now I want to see if I can factor this guy. Leading coefficient here is just 1, so I'll say L, and L, this could be, well, it could be 3 and 7 or 3 and 7 that way. This says the signs are the same, and this says they're going to be negative. Looks like I could put a negative here and put my 7 and a 3 in there, and then when I FOIL this, first times first is L squared, last times last is a positive 21. Outer -3, inner -7, that combines -10, that looks good. So I have L minus 7 equals 0 and L minus 3 equals 0, or L equals 7 or L equals 3. Okay, so in that case, L could be whatever side I want. I've said that's the length, so I'm going to call that 7, and the other one is going to be then the value of 3, isn't it? And I can go ahead and check that. Now, sometimes you go through these kinds of equations, you might end up with a negative value. And anytime you come up with a length that ends up as a negative value, you want to make sure you say, well, that's not valid. I can't have a negative length. In this case, they're both positive. Okay. So we're going to say then that if L is 7, we can solve that and get W equals 3. And if L is 3, we can come back and say the other variable is 7. But by convention, we say length is the longer one. So we'd say, well, here's 7 and here's 3. And here's our rectangle here. Okay, it makes sense. Questions on what we did there? Okay, I'll take that as a no, we didn't have any questions. All right, let's try, which one haven't we done here? Let's try another one here. Let's try y equals x squared plus 5 and x squared plus y squared equals 25. Okay. So given that, let's see if we can work our way through. And what are we trying to do? We're trying to solve these, aren't we? We've got 2 equations, 1, 2, and 2 unknowns, x and y. Okay, now we can solve by substitution. Okay, if we solve by substitution, we could substitute this value for the y squared value, couldn't we? If we wanted to. Okay, if we solve for x, we could do that as well. So let's see here. We talked about solving by substitution and solving by addition or elimination. Now you'll notice that if I solve for y and start substituting back in here, then I'm going to have squared terms, and it looks like it's going to maybe get a little more complicated than I want it to be. And I'm always, at least when I'm doing them, I'm looking for the simplest way to solve these. So I might say, you know, it might be easier. I've got an x squared here, and I've got an x squared here. Maybe I should set these up so I can eliminate the x squareds. So let me rewrite these equations. And let's just put them in terms of x plus y equals some constant. So if I rearrange this, x squared minus y equals -5. Okay, bring the y over and bring the x over. So x squared minus y equals 5, and x squared plus y squared equals 25. Okay, so I've got these, and I want to eliminate the x. So if I subtract this, I could say, well, negative, 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 and then subtract. And these go away, and I'll get negative y squared, negative y equals a negative 30, it looks like. Okay. And now they're all negative. I guess I can just multiply through by -1 and make them all positive. So now I've got y squared plus y equals 30. Looks a little more comfortable. So I bring the 30 over and I say y squared plus y minus 30 equals 0. That looks like something I might be able to solve. Again, leading coefficient here is just a 1. And here it's a 30. So I guess that could be 1 and 30 or 2 and 15 or 3 and 10. 5 and 6. Could be a lot of different combinations here. This says the signs are opposite, and this says the larger is positive. So I've got y and y, and I've got just a 1 here. So that when I FOIL this, outer gives me y squared. Any of these combinations will give me 30. So I could put any of these in here. But when I combine outer and inner, I want just 1, don't I? So 15 and 2, we can't sum those to get 1, can we? 15 plus 2 or 15 minus 2. That doesn't give me a 1. 10 and 3, that's 13 and 7. That doesn't give me a 1. 6 and 5 is 11 and 1. Oh, that'll give me a 1. So if I put a 6 here and a 5 here, the signs are opposite. The larger is positive. So I could say positive 6, negative 5. When I FOIL it, it works out, doesn't it? So now I can solve y plus 6 equals 0. Y minus 5 equals 0. Y equals negative 6. Y equals 5. So I've got 2 values for y. So if I use y equals negative 6, and over here I'll use if y equals positive 5. What am I going to get from my x values? So I had my equation above on y equals x squared plus 5. Let's see here. X squared. So I have y is negative 6. I have a negative 6 equals x squared plus 5. Let's see. X squared. What did I do here? It doesn't look right. If y is equal to negative 6, then x squared. All right, let's try using one that might help us a little more. Let's do this. Let's say if y is negative 6. Yeah, well, no, let's just do it. Let's just do it. Negative 6 equals x squared plus 5. Let's just use that one. So x squared equals negative 6. Bring over here is negative 6, negative 5, negative 11. Okay. So x squared equals negative 11. So x equals the root of negative 11. Well, when we take the root of a negative number, we're really doing root of negative 1 times root of 11, aren't we? And the root of negative 1 is defined as I, isn't it? So x equals I root 11. And when we have the I root 11, that really just says that we've got an imaginary number here, don't we? Because this root of 11 can be a positive or negative value here, can't it?
I was just about to ask it. It can be a positive or negative, right?
Yes. Yes, because we're taking the square root.
Right.
Okay.
It's still an imaginary number, though.
Yes, it is. Yes. All right. So that's one set of values that can be used over here. If y equals positive 5, we'd say, well, let's see. 5 equals x squared plus 5. 5 on each side. Those are going to cancel, aren't they? So x is going to be equal to 0. So we have a situation that if y is negative 6, x can be plus or minus I root 11. Okay, and if y is 5, x is 0, so we have 0 and 5. Okay, so here, depending on how the question is phrased, this is not a real solution, is it? So it is a solution, but it's not a real solution. That is to say, we don't find this value on the real number line. But a real solution could be 0 and 5. So we could say here is a solution that it is a real solution. Both solutions, but this is not real. It's on the imaginary axis. Okay, questions on what we did there at all? Solve by elimination and substitute values back in. Okay. All right, if there aren't any questions on that, I'm going to continue. If there are, I'll take your questions. Okay, let's see, what one haven't we used that we can solve here? We did that. How about, let's see, maybe we should use a, let's do one that looks like this. Equation 1, equation 2. X squared equals 2y plus 10. 3x minus y equals 9. All right, now one of the things we want to do when we're looking at this kind of a problem is decide, what would be a good way to solve this? Would we use substitution? Would we use elimination? Which one do we want to use here? And we have 2 y's and 1 y, and we could solve for y, so we could do it either way, couldn't we? We could solve for y and say y for equation 3. We could say y equals 3x plus 9 and substitute back in here. And I guess we could also combine these and try and eliminate the y with elimination. So it looks like we could do it either way. So let's just try substitution first, see how that works. So we get y equals 3x plus 9. So x squared equals 2, 3x plus 9 plus 10. X squared equals 6x plus 18 plus 10. X squared minus 6x minus 28 equals 0. Is that right? That's 28. Bring it to the other side. Bring this to the other side. So we have to ask ourselves then, is there a value we can use then to solve and get to solve this thing? And let's see here. Well,
Wait, would it not be a -9?
Where am I looking here? Well, yes, you're right. Thank you. -9. So this is a -9. So this is a -18. So now we change this value, don't we? So 18 and 10. So this is going to be a negative. Is that right? 2 times 9 is negative. Looks like that's -8. Does that look right? And I took 2 times, this was, I think I've got everything mixed up here. X squared equals, well, maybe that's right. 6x. Well, I don't know. Let's before we go any further, let's make sure this is correct. Do we think this is correct, or have we made a mistake? What we're trying to do, now this is interesting because it looks like it's simple. We're going to take this equation and substitute in here. So let's simplify that first equation. What should it look like? X squared minus 2y equals 10. That's this first equation. And we're going to substitute for y. So x squared not equals minus 2 times y, and y is 3x minus 9. And that's equal to 10.
I think the 8 is supposed to be positive when they're all on the left side.
Well, let's see if that's true. Let's just take a look here. So we took our first equation and brought it down here. Do we agree with this? We brought the y over and the 10 is there. That's good. Substitute the 3x minus 9. That looks good. So this still looks good. X squared minus 6x plus 18 equals 10. Negative times a negative is a positive. That looks good. Now, if we bring this 10 over, we'll get x squared minus 6x plus 8 is 0. And then we want to factor this thing, don't we? So this is a 1 and a 1. This is a 1 and an 8, or a 2 and a 4. So we know it's going to be x and x. Signs are the same, and looks like they're both negative. So we'll put a negative here. And if we put an 8 and a 1, we can't combine 8 and 1, get 6. 8 plus 1 is 9, minus 1 is 7. 4 and 2 is 6, that works. So if we put a 4 and a 2 there, if we FOIL that to check it, we get x squared, that works. Positive 8, that works. And negative 2, negative, that looks good. So x minus 4 equals 0. X minus 2 equals 0. X equals 4, or x equals 2. Okay, and then we have to solve for the y values, don't we? So if we solve for the y values, what do we have here? Well, we can say 3x minus y equals 9. If x is 4, 3 times 4 minus y equals 9. Or 12 minus 9 equals y, or y equals, is that 3? Let's see, 1 minus y, 12 minus y equals, not y, equals 9. This is a y. So y equals 12, looks like y equals 3. Is that what you guys get? So when x is
Yeah.
4, yeah, x is 4, y is 3. Is that what you guys get? 4 and 3?
Yeah.
Okay. And then when x is 2, put a 2 in here. 3 times 2 minus y equals 9. 6 minus y equals 9. 6 minus 9 equals y. So that's going to be negative 3, isn't it? So when x is 2, it's negative 3. Okay, so now our solution set then, if we put it in solution set form, we can say we have a 4 and a 3, or we have a 2 and a negative 3 for x and y. Okay, so same kind of thing. We have to determine whether we want to solve it by substitution or elimination. We went through and solved it by substitution. We could also go through and solve it by elimination. Maybe it'd be easier, I don't know. We multiplied this by 2. So we'd get 6x minus 2 equals 18. And we're combining that with, and that's 2y, 6x, 2y. And here we've got x squared minus 2y equals 10. If we subtract these things, we'll change the signs. And we'll get negative x squared plus 6x, the y's go away, equals 8. And if we make this positive, x squared minus 6x plus 8, it looks like we end up with the same values here, doesn't x squared 6x. Here we end up with a minus So we bring the 8 over, I guess we end up with a -8 equals 0. So I guess we ended up the same way. You'd have to determine whether you think this is an easier method using the elimination method going this way or the substitution method and coming this way. Looks like this is actually a little simpler. Okay, but we're going to end up with the same answer, whether we do it by substitution or elimination. Okay, questions on that at all? Okay. Let's see if we've got one more we can get in before we take our break. Let's say we are given the following situation where we have some sort of an area like this. And you're given, and let's say we want to put a divider right here. And let's call this distance X. So that's X and that's X and that's X. And then let's call this whole distance here Y. Okay. And the problem says you're given so much length. Maybe this is fencing. And you're given so much length of fencing. And so it might say given length equals 36 feet. That's the total amount of length you have here. So if we add this, plus this, plus this, plus this, plus this, that's going to equal 36 feet. Okay. And you need to enclose, so we need an area is given as, let's say 54 square feet. And the idea is, can we figure out what the values of X and Y should be, given that we need a total area of 54 square feet and a total perimeter of 36 feet. And we could say, well, let's see, what methods can we use to figure this out? We could say, well, how many X's do we have? We have 3 X's plus 2 of the Y's. And that has to equal how much? The total perimeter, right? Maybe I should call that perimeter, which is 36. So that's one equation where we have 2 variables, so we need 2 equations. So another equation we can get from the area, and the area is X times Y equals, and we're given that's 54 square feet. This is feet. All right. So the idea is then, can we solve this equation for X and Y? Okay, are we able to do that?
I believe so.
All right. Who wants to give me a suggestion? Give me a new volunteer to give me a suggestion of what we might do here. Jacob, what do you think? Jacob's not helping us. Justin, what do you think?
We could multiply equation 2 by 2.
We could, times 2. Okay, and what are we going to do when we get that? What is that going to do for us? Or call on a friend. Now, keep in mind, I think when you said let's multiply by 2, I think you might be thinking, hey, we've got 2y here, and that'll give me a 2y here. But these aren't pluses, are they? These are multiplies. So we're not going to be able to combine equations 1 and 2 by adding or subtracting and getting rid of a value. So this may not be our approach. But we certainly could solve for y or for x. We could say y equals, or we could say x equals, couldn't we? We could say x equals 54 over y, couldn't we? And then we could substitute that back. So that says 3x plus 2y equals 36. And if we substitute for x, if I put 3 times 54 over y plus 2y equals 36. Now we have one equation and one unknown, don't we? But we have a y in the denominator. So what method do we use to get that out of there? Don't we multiply through? So let's see, 3 times 54, 162. So let's say this is 162. Let's say I multiply through by y. So y here, y here, y here. These y's will cancel, won't they? So I'll get 162 plus 2y squared equals 36y. Maybe rewriting that. Well, maybe before I rewrite, I should divide through by 2. So 162 over 2, what's that going to be? 81 plus y squared equals 18y. Does that look right? Okay, and then putting everything on the same side, y squared minus 18y plus 81 equals 0. If our arithmetic has been correct here so far, then we could factor this thing, couldn't we? And keep in mind, we're looking for lengths now. So if we come up with any negative values, we don't want to use those. So here we have a y and a y. That'll give me y squared. And this says that the signs are the same and they're both negative. And the factors of 81, well, let's see, 9 times 9 is 81. So y minus 9 equals 0, or y equals 9. That works, doesn't it? So let's just see. If y equals 9, then this distance here is 9. And then we want to find out what x is. Well, we know above that x times y equals 54. If y is 9, that says 9x equals 54. 9 times what? 6, huh? 9 times 6 is 54. So x equals 6, so this value is 6. 6, 6, 6, that's 18, and 9 and 9 is 18. That's the 36, that checks. And 9 times 6 is 54, that checks. So it looks like our solution then would be to have the values for the y value 9 and for the x value 6, and we're able to solve it using the system of equations and doing substitution. Let's see, what time is it here? It's 4:01 by my clock. Does 5 minutes work for you guys?
Yep.
All right.
Yeah, that works.
See you in 5 minutes.
Professor, quick question.
Yeah.
Are we doing 7.5 and 7.6 or just 7.5 after?
We're just going to do 7.5.
All right, sounds good. Thank you.
7.1, 7.2, 7.4, 7.5 is all we cover. Are we ready to continue? Are there any questions that came up at the break? Okay, well, let's finish up with the 7.5 and we'll be out of here. And then let's see, before we do that, so Monday, the 6th, we'll do 8182, and then that'll be it. And we'll just kind of answer whatever question. The final covers the entire course. So we'll just kind of take whatever questions you might have on anything we've covered from section P through chapter 1, chapter 2, chapter 3, chapter 7, and chapter 8. Just the sections that we've covered. 1, 2, 4, and 5, and 1 and 2 here. Okay, that's what the final is going to cover, the whole works, and that'll be for an hour and 50 minutes. So let's see. In this section 7.5, we're going to talk about systems of equations and the inequalities. And we're going to see if we can graph the linear equalities and the nonlinear equalities and see if we can take a look at what they look like here. So let me get some paper here. And if I were to say, what does it look like if I graph I want to graph 4x minus 2y greater than or equal to 8. Maybe that's what I'm trying to graph. So I'm going to set up some xy coordinate plane here. And some things that I want to be aware of is whenever I'm saying greater than or equal, I have to pay attention to what this graph is going to look like when I say that. So I might want to solve this and put it in the form y equals mx plus b. So I can kind of see this is going to be a line, isn't it? And we want to see what that line is going to look like. So I might say, moving the 2y to the other side and bringing the 8 over, I might say 4x minus 8 greater than or equal 2y. I just added 2y to each side and subtracted. And then I'll divide through by 2, and I'll get 2x minus 8 is greater than or equal to y. And just for comfort, I might want to say y then is less than or equal to 2x minus 4. This should be a 4 here. 8 divided by 2 is 4. So what I've done is I've changed the form of this equation to y less than or equal to 2x minus 4. Now I might want to take a look at what that looks like. So I might set up a table of values and say x and y. And maybe I'll graph, I don't know how many values I'll put here. -2, -1, 0, 1, 2, 3, 4. Let's see what these look like. So if x is 0, we're at -4. X is 2, we're at 0. So those are easy ones. X is 4. Let's see, 4 times 2 is 8. So that's going to be 4 again, isn't it? Back here the other direction, x is -2. That's going to be -4. That'll give me a -8. And looks like this is a -6. And this is negative. So it looks like we're going up by values of 2, doesn't it? So -2, 0. That looks like a 2 and a 4. So if we plot these, let's see if I go, if I call that 8, 4, and -4, -8, and 1, 2, 1, 2, 3, 4. it looks like I'm going to look sort of like -2, -8 is here. And -1, -6, so I'm going to be roughly here. 0, -4, 0, -4 is here. And a 1 and 2 and 2 and 0 and 3 and 2 and 4 and 4. So it looks like I'm going to have a line that's, let me get a straight edge here. It looks like it's sort of straight. If my graph were better, it would be straight. It sort of looks like that. And I want to graph all the values. Now, I want to solve for this. I drew this line right here, and this line looks like the line y equals 2x minus 4. So when x is 0, we're at -4. So this line is this equation here, which is this equation here. And we want everything where y is less than that line. So we're looking for values where y is less than that line. So two things we want to think about. One, is this line a solid line or is it a dashed line? And it's a solid or a dashed line depending on this sign here. This says values less than or equal. Less than or equal says we can be on the line. So if we can be on the line, then the values on the line are included, and I'm going to make that then a solid line. So I'm going to put a little note here and say that indicates a solid line. And I have I've constructed my line. And let's just say then here's my line. It looks like that, and it is a solid line because of this value here. We put in our points, and I want to label these points 4 and 4 and 3 and 2 and 2 and 0, 1 and -2, 0, -4, -1 and 6, and so forth. So here are the actual points. Okay, those are the points on that line. So the points are good from my table of values connected with a smooth curve. It's a straight line of the form y equals mx plus b, where m is 2, b is -4. So everything looks good. And now I'm trying to find out, well, because I want to cover the points, all the points where y is less than or equal to, what's that going to look like? Well, let's just pick a point and find out then what side of the line I'm going to cover. So I'm going to pick an easy point here. I'm going to call this a test point. Right here, 0, 0. So I'm going to say test point 0, 0. So if I put that into my equation, let's see what I get. My equation was 4x. Well, I'll use this one right here. I'll use the simplified version here. 2x minus 4 greater than equal to y. So if x is 0, 0 minus 4 greater than equal to 0. Plugged in 0 for y, 0 for x. Then I'm saying, is this true or false? So -4 greater than 0. That's false, isn't it? So if that's false, this point is not included in this graph. In the graph 4x minus 2y greater than 8, this point is not included. So that means that points on the other side of the line are going to be included. I could put in test values down here and find out if they're true or not. I could go down here to 4 and 4. I could test that value. But I'm going to find that those values are true. So what I'm going to say then is that when I color this in, if I do it from here to here, then this shaded area here that I have represents the equation when I've asked to graph 4x minus 2y greater than equal to 8, that this is what the graph would look like. Okay, and how did I find it again? Solve for y, draw a y equals line, put in a table of values, connect the dots, find a test point, find out if that test point is in this area. If it's true, if this test point is true, it's in the area. If it's false, it's not in the area. Why did I pick this? Because it's easy. 0 is an easy one to evaluate. Okay, when I plug 0 into the equation. Okay. Questions on what we did there?
So if a point on one side is false, does that automatically mean that the other side is true?
Yes.
Okay.
And you could always check a point on the other side. We could take a point. Here's a value over 2 and down 2. We could say over 2 down 2 and say test a point 2, -2, and put that into the equation. And we'll find that that's going to end up with a false scenario. Okay. Well, let's just do it. 4 times 2 minus 8 is greater than 2 times -2. So 0 is greater than equal to, what is this, 4? That's supposed to be, which direction are we going here? 4 times x is, that's not -2, that's +2, isn't it? 4 times 2, okay. Minus 2 times -2, that was, that's what is it supposed to be here? All right, plug in the value here. Let's see, we plugged in 0, 0 because it was easy. And we ended up with 0 for x, 0 for y. So if we plug in 2 and -2, let's try that. 2, well, let's use the one we used above. Y less than equal to 2x minus 4. Let's see if that works. Y is -2 less than equal to 2 times 2. That's 4 minus 4 is 0. And that's 2 less than equal to 0. That should be true. Well, they can't both be true, can they? They cannot both be true. If we were to test this value and we get a false, and test this value and we get a true, we're okay. If we test this value and get a false and test this value and get a false, something's wrong with our arithmetic. But we tested our point over here, found out it was false, tested our point over here and came up with -2 less than 0, which was true. So this is true. This was false. So points on, and we could, if you want to convince yourself, you can take any number of points. And anytime you're on this side of the line, including points on the line, 4 and 4, 3 and 2, any of these points on the line, because we've said greater than or equal to. And when we solved it for y, we said y less than or equal to. So less than y. So y is going up this way. So here's positive y, here's greater than, here's less than. Okay. Questions? Okay, I'll take that as no questions. Let's try another one. Let's say I have a simpler equation. Maybe I have y, and I say greater than -3/4 x. Now, the fact that I've said greater than that says the points on the line are not included. Okay, so points on line not included, which means we're going to represent that with a dashed line. Dashed line might look like that, saying that the points that are on the line that represent the line, they're not included in our solution. And we'll come up with a test point like we did before. So that we're going to go through the same kind of a procedure. So let's create our table of values and plot this thing. So here's a table of values. Here's X, here's Y, and -3, -2, -1, 0, -3, -2, -1, 0, 1, 2, and 3. So if we take a look at what that is, -3, if I put in a -3 here when I do my calculation, I came up with a 2¼ I'm going to, rather than calculate each of these, I previously did my calculation. And I came up with, you could do your calculations right now if you want. For instance, an easy one, X is 0. If X is 0, this whole thing is 0, isn't it? If X is 1, it's -3/4. If X is 2, it's -1½. X is 3, it's -2¼ So those are my points that I can plot. And if I were to plot those points of the form y equals mx plus b, well, b is 0, isn't it? So we know it's going to go through here. And so here's -3, here's +3. And let's say we have 1, 2, 3, 1, 2, 3. So -3 and 2¼ -3, so roughly here, -3 and 2¼ -2 and 1½. So here's -2. That's roughly here. -1 and 3/4. So -1, or up about 3/4. So here. Zero and 0, 1 and a -3/4, 2 and 1½ and 3, 2¼ So we should end up with a line that runs roughly like that. Here's 1, 2, 3, -1, -2, -3. And this is at 3 and -2 and 1/4. And this is at 2 and -1½. And this is at 1 and -3/4. So I've labeled all my points here. And a 0 point here. And when I draw this line, I said, these points are not included. So I connected that with a straight line curve, but the actual line that I'm going to draw is a dashed line because that says those points are not in the solution. And I want y greater than. So we can pick a test point. Easy test point might be over 1, up 1. I might pick this point right here, 1, 1, as a test point. So 1 greater than -3/4 times 1. So is 1 greater than -3/4? Is that true or false? Well, 1 is greater than -3/4, isn't it? So that's true. So that test point is in the area that's true, which says then that my solution is over here. It's above the line over here. So what I've colored in here is the solution area, not including these dashed values on the line here. So it's any value up this direction when it gives me a positive test. If I take a -1, -1, I should generate a false positive one, I should generate a true. Questions? See what we're doing. We're talking about graphing these inequalities. Okay, let me give you one and you guys can do it. Let's say I give you a y greater than 1. And here's my xy coordinate plane, and I'm saying graph. Okay, do we know what that's going to look like? First of all, will it be a dashed line or a solid line? New volunteer. Or I can call him.
Dashed line,
Dashed line. Why do we say dashed line?
because it's just greater than it. It's not greater than or equal to.
Correct. Okay, so we're going to say it's a dashed line. So it's going to be a line that sort of looks like that because the points that we're going to plot are not going to be on that line. All right. Now, if we were to plot, not greater than, but if we were to just plot y equals 1 with a table of values, x, y, x is minus 3, x is 0, x is plus 3. So if I were to plot x is equal to 3, here's 3, here's negative 3. If x equals positive 3, what's y? And here's what we're plotting here. And we want to plot this for x equals 3, for x equals 0, and for x equals a negative 3.
It would be 1.
It'd be 1. So x is 3 and 1. So we have a point here at 3 and 1. How about when x is 0? Same?
Yeah.
It's 0 and 1. And when it's negative 3, it's the same, isn't it? Negative 3 and 1. So we're going to have a line that goes through here. It's going to be dashed. So if I were to do this, so that's the line. It's going to be coming here. It's going to be dashed because the points that we're going to plot are not on the line. And then we need a test point to find out which area we shade. 0 is always a nice test point. So if I say 0 greater than 1 as my test point, y equals 0. 0 greater than 1, is that true or false? Well, it's false, isn't it? 0 is not greater than 1, so that's false. So this area down here is false. I guess I could pick a point up here. I could pick 2. 2 greater than 1. That's true, isn't it? So that says my true values are all up in here. So I could say, well, then up here is where they're going to be the true values are. And I could highlight them with this kind of a hash mark if I wanted to. But so if the problem says graph this equation, well, set up our XY coordinate plane. We're showing our work over here. We don't have to put a box around and an arrow to graphs. I can read your graphs. I'm not asking you to put a box around that. Okay, so that would be the solution for that problem. Okay, questions on what we did there? Okay, how about a similar problem that says x, what should we say, greater than, no, let's say less than. Let's say x less than or equal to negative 2. X less than or equal to negative 2. What are we going to do here? X, y, 2, 1, 0, -1, -2. So we might want to determine, let's see, this says it's going to be a solid or a dashed line. That's a solid line, isn't it? Because we include the points. We include those points. Okay. So what is the line x equals, and I'm going to say graph here. So what does the line x equals -2 look like? Table of values, x, y, x is -2. So x is -2 no matter what y is, right? There's no y component here. So x is -2 regardless of the value of y. X is going to be -2. And we said it's a solid line. So I'll represent a solid line in blue here along the line x equals -2. So that's that. And then our solution, well, we better pick a point as a test point and see what that's going to be. 0 is always a good test point. So let's say x equals 0 as a test point. So our original equation was x less than or equal to -2, and 0 is our test point. Is that less than or equal to -2? Here's the point we're testing up here. Here's our test point. So is this true or false? 0, well, 0 is not less than -2, it's greater than, isn't it? So this area over here is false. I guess we could do a -3 and test that. X equals -3. Is -3 less than -2? It is, isn't it? So this area over here is true. Okay, so if we were to shade that, we could say the areas over here are true, including the line, because we have less than or equal. So here's less than or equal. Questions? Okay. How about if I have an equation that looks like the following? X squared plus y squared greater than or equal to 16. How are we going to plot this? Do we know what that looks like? New volunteer, do we know what that looks like?
It looks like a squared plus b squared equals c squared.
A squared plus b squared equals c squared. Okay, the Pythagorean theorem, is that what you're saying?
Yes.
Okay, so this represents a triangle. Looks like this, where this is A and this is B and that's C. Is that kind of what we're thinking?
Uh-huh.
Okay, well, let's try that out and see what we get. So let's set up a table of values in X and Y. And let's say X is 0. Well, let's see, we'll put in some negative values here too. -2, 0, +2. Let's just see how these work. So if I put in -2 and square that, I'll get a 4 plus, and for y, I can put in, I guess I could put in the same values, couldn't I? Whatever I wanted to. Square that, that's 4 greater than equal to 16. So if x is -2 and y is -2, here's -2, -2. So I have a point right here at -2, -2. That's this point here. And we put it in our equation and we test and we say, is 8 greater than or equal to 16? And what's the answer? Is that true or false? False, isn't it? 8 is not greater than 16, it's less than, so that's false. So what this says is this point is not within the solution. Now, this relates to a right triangle. This is Pythagorean theorem that relates to the sides. The square of the sides of a right triangle is equal to the square of the hypotenuse. That's not this. This is what we get when we take a, let me just draw it here. If I take this and go like this and pick a point over here and draw a right triangle, and this point is XY, then I can say that's point X, that's point Y, and here generally was referred to as the radius of the circle, isn't it? Which is the hypotenuse of this right triangle. So we can say x squared plus y squared equals 16. We could say if this is if we square this value and square this value and get 16 is 4 squared, we could say this r value is equal to 4, couldn't we? 1, 2, 3, 4. So this point out here, if we swing this radius down, becomes 4 and 0, doesn't it? And over here it's 0 and 4. And over here it's -4 and 0. And over here it's 0 and -4. So we've got 4 points around this circle. So my point was this represents a circle. So as we change x and y values, this r value remains constant. This doesn't change. So if we say, what does this equation looks like? It looks like a circle. Okay, and here's my circle.
Professor, I didn't get how this problem works. Could you repeat another problem like this?
Well, we're not done with this one yet.
Oh.
We're just going through it. What we're asked to do, what this problem asks us to do, is graph this equation, x squared plus y squared greater than equal to 16. That's what this problem is asking us to do, and that's what I'm taking us through right now. We're not finished. So we should recognize, first of all, that this is a circle with a radius of 4. 16 is 4 squared. X squared plus y squared equals r squared is a circle. So if this is our circle, and this says that the points that we're going to plot, which are here and here and here and here, and we could pick any other points if we wanted to, that says those points are on the circle. So I'm going to make that a solid, because any points that we select are going to be on that circle. So here's the graph of the circle. This is the graph of x squared plus y squared equals r squared, which happens to be 4 squared, which is 16. That's this graph right here. If you were asked to graph x squared plus y squared equals 4 squared, you'd say that's the graph of it. Now, if you were to say graph this equation where x squared plus y squared is greater than 16, we would use the same techniques that we've used earlier, which says graph this equation, which we just did, and then pick a test point and say, is that test point within the solution? And 0 is always a good test point, isn't it? So let's pick the point 0, 0. So my test point is 0, 0. So x equals 0, y equals 0. So if I put that in my equation of what was given, x squared plus y squared greater than equal to 16, if I put 0 plus 0 greater than or equal to 16, 0 squared plus 0 squared, that's 0 plus 0, that's 0 greater than 16, true or false. Is 0 greater than 16? It's not, isn't it? It's false. Which means at this point and any other point in here, we could pick other points if we wanted to, you're going to get the same answer, which is a false. So that says nothing inside this circle relates to the graph of the equation. Okay, which means that the true area is outside of the circle. So the true area is going to be anything out in here. That's where our solution lies. So if I put a box around this and say it can go on forever, but it says anything out here is true. Anything in here is false. So this is the true area. This is the false area. Okay, questions? We went through it the same way. We looked at this and said, it's a solid line. We graph it, take a test point. We can take any test point we want, inside or outside, but we might as well take an easy test point, for instance, 0. So X and Y are both 0, 0 greater than 16. No, that's false. So none of these areas are included. Solution is outside, so the solution is all out. All out in here is the solution. Okay, and you could show a solution either by coloring it or you could put hash marks, whatever you want, but this is false. This is not in the solution area. Okay. Now these become a little more interesting if we have a couple of equations. For instance, you might be asked to graph something that looks like, let's get a new piece of paper here. Maybe you're asked to graph the following. X minus 3y less than 6, equation 1. And equation 2 might look like 2x plus 3y greater than or equal to negative 6. The idea is we want to graph these two equations. You notice that they're both linear. They're both, if we were to solve them, they're of the form y equals mx plus b, aren't they? So they're two straight lines. But in order to solve this, we're going to have to figure out what the lines look like. And we look at this first line here, and that says this line is the dashed line, isn't it? Because the points are not on the line. And this line is a solid line because the points on the line are included. Okay. So if I were to graph these, I could solve this for y. What do I get? 3y. If I make an equation out of it, x plus 6, divide through by 3, and I get y equals x over 3 plus 2, or 1/3 x plus 2. So that's what that first line looks like. Maybe I'll call that equation 3. Equation 4, I solve for the second line and say, well, what does that look like? Well, let's see here. That's 3y equals negative 2x minus 6. Y equals negative 2/3 x minus 2.
Professor, wouldn't the first equation be y equals 3y equals x minus 6?
Is that a minus?
Uh,
Let's see here. 3y. Yes. Yes, it looks like that would be. Let's take a quick look here. Is that true? Minus 6. Bring this over and this over. Yes. Yes. Yeah, through 2x. And for this one, 3y, we brought that over. Yes, that should be negative, shouldn't it? Which means this is going to be negative. Okay, so we're going to have y equals mx plus b, where m equals 1/3 and b equals -2. And we could kind of rough that in, -1/3 and -2. So over 3, 2, 3, and down 1. So it's going to be roughly something that looks like that. And it's solid. Let's see, which one did we graph here? No, this is going to be, that's going to be dashed, isn't it? Because it's, so it looks like that's going to look something like that. Did I do that right? If I need to solid that in, I will. Let's see, y equals, make sure we've got that correct here. Let's solve this one again. 3y equals x minus 6, 1/3. So that's going to, this is a positive slope. So I'm going to get another piece of paper and make this drawing correct. So we have a positive 1/3, 1, 2, 3, and we're down 2. So we're going to start here and go over 1, 2, 3, and up 1. So it's going to be roughly here. Y equals 1/3 x minus 2. We'll call that line. And we started out with a less than or equal. So we're going to say that's a dotted line. So here's x, here is y. And let me write these equations up here to make sure we know what we're doing here. So equation 1 started out as x minus 3y less than 6. And when we solved it, we said 3y equals x minus 6, or y equals x over 3 minus 2. And that's this line here. And this says that we don't include the line. So the line comes through here. We can plot, we could put a table of values and plot all that if we wanted to. But we would end up with something that looks like this. And then the second equation was, let's see, what was it? 2x plus 3y greater than or equal to -6. And solve this one, 3y, and I'm going to plot equals -2x minus 6, divide through by 3, and I'll get y equals -2/3 x minus 2. So it looks like this one is going to have a negative, and we're going to include it. We're going to include the points. So at x is 0, we're down here at -2. So we're at the same point right here. So that's 0, -2. And we're going to have a slope of -2/3. So we have a rise of -2, a run of 3. So 1, 2, 3, down 2. So it's roughly going to look something like that. And it's going to be solid. All right, so we're going to have those two. Now we could plot actual points by setting up a table of values for each of these for x and y, and plot some actual points, label the points and so forth. But what I'm going to do in this one is just say, if we're asked to graph two equations, one looks like this and one looks like this, then I can say, well, here's this graph of this one, and here's the graph of y equals -2/3 x minus 2. That's this one. To put up some actual values here, if we're asked to put up actual values, then we would have to put up a table of values for each curve. and solve for those points. But here we can say, well, we're going to be down here at 0, -2. Here we have a slope of +1/3, and it's a dashed line. Here we have a slope of -2/3, and it's a solid line. And now we have to say, well, where is our solution? Is it here? Is it here? Is it here? Is it here? Where are we looking for our solution? And we do it the same way, right? We look for a test point. And 0 is always a good test point. So let's let x equals 0 and y equals 0 as our test point. Okay, so if I say in the first equation, x minus 3y less than 6, 0 minus 0 less than 6, true or false? Well, 0 is less than 6, isn't it? So that's true. So we know that is in the solution area. We could say then the solution is going to be somewhere. That's a good solution area. How about something over here? Well, let's see, we could go over 1, 2, 3, 4 and down 1. We could pick a point here at 4 and 1. Let's see what that looks like. So we have 4 minus 3 times 1 less than 6. And let's see here. 4 minus y. Oh, this is a -1. You guys got to make me honest here. So that's 4 -1, not 4 +1. So 4 negative times negative is a positive. That's 4 plus 3 less than 6, 7 less than 6. Is that true or false? We know that's false, don't we? So this test point here is false. All right, so this is not included. We could take a look at a point down here, 0, 1. So we could take a look at here at 0, -3. So we had x minus 3y less than 6, 0 minus -3 less than 6. And that's 3y. So that would be positive 9 less than 6. 3 times 3 is 9. Negative times negative is a positive. 9 less than 6, true or false? 9 is not less than 6, is it? That's false. So this area is false. And we could pick a point over in here. -1, -2, maybe -4 and 0. Hopefully that's going to be far enough out. X minus 3y less than 6, -4. And this is 0. Let's see here. -4 and 0. Is that going to work? And for that is less than. Doesn't look like that's working for us. Maybe this point isn't far enough over. See, I didn't actually graph that. If we put in -4, what do we get? -4 minus 3 times 0 and less than 6. -4 is less than 6. So if we go farther over here, are we going to end up with, how about if we go over here, -8? -8 and 0. They're all going to be. So that says that our solution area would include values over here. That doesn't seem to be right. So I think we've done something incorrect here in terms of our equations. 2x, 3y greater than equal to -6. Oh, greater than, oh, let's try that. 2, or is that greater than -6? No, that wouldn't be. if we have the equation 2x plus 3y greater than or equal -6, and if x is some large value, x is, what do we say here, negative, well, let's just try -6, 2 times -6 plus 3 times 0 greater than or equal to -6. 2 times -6 is -12. 3 times 0 is 0. Greater than or equal to -6. -12, that's true or false? That's false. Isn't -12 is not greater than -6. So that's false. So that this area is a false area. That's all we were trying to prove. Generally, you don't have to do that. Generally, you pick an area, say this 0 point, pick an easy number so that you can simplify the equations. And we said that was true and all these others were false. So as we go to graph this then, if we were to color it in, we could say, well, all this up in here is the true area, including the line, this line here, not including this line here. All right, so this is a dashed line, this is a solid line, and the true values are up in here, including this line, not including that line.
So I had a question.
Yeah.
So if we put in the values -6 and 0 into the equation x minus 3y is less than 6, we get a true result. So would we have to always test both equations?
We need to test both equations. Now, if we are testing this equation here, and we're testing for greater, that's going to be true, isn't it? Because anything greater than that line is going to be up in here. So if anywhere we go over in here, we are going to be true on that line, but we're not going to be true on that line. Okay, and we're asked to graph both these lines. Okay. So here's the one line, and for this dashed line here, any of these areas here are true for that line, but not for the combination of the two lines. When you're asked to graph the equation of these two lines look like this and like this. And we're looking to be above this line and above this line. And we're looking to include these points, not include these points. Okay, so when we're looking at the specifics, that's a false area for both lines. That's a false area for both lines. So is that. The only one true for both lines is this one up in here. Does that make sense?
Yeah, thank you.
Okay. I'm going to take you through one last problem, which I think you'll find is interesting. It looks like this. I'm going to give you 3 equations. X plus y less than 2. It's going to be a dashed line, isn't it? That says it's a dashed line. I give you another equation that says -2 less than or equal to x less than 1. So you notice here, it's a solid line. Here it's a dashed line. And then I can give you another one. I can say y greater than -1, greater. So now what I need to do is be able to plot. I need to plot these 3 equations, equation 1, equation 2, equation 3. And I need to plot them on my XY coordinate plane, see what they look like, and then find the solution area. Okay, so if I plot this first equation, it looks like y equals -x plus 2. Okay, so that says, let's see here, 1, 2, 3, 4, 5. We'll go up and down 5 and maybe go over, I don't know how far we'll go here, -4, +4. So if I plot this, y equals -x plus 2. So here's +2. -x is over 1 and down 1, isn't it? Over 2 and down 1. So we're going to have a line that kind of comes through here like this. It's down, and we don't include that, so that's going to be a dashed line. And so I'm just going to leave that kind of a light line there. Let's just see what that looks like. So we're going to have a line that comes through here. Now, if I plot this second equation, x is greater than -2 and less than +1. +1 is here, -2 is here. Here's -2, here's +1. So x is greater than or equal to -2. That's going to be a dashed line, isn't it? So that's going to be a solid line here. This will be the dashed line here. This was a dashed line here because it was a less than value. So that's dashed. This is dashed. This is solid. And the last one, y greater than -1. Here's -1 here. And it's dashed as well. So if I plot these, it looks like this is solid. This is dashed. And this is dashed. And this is dashed. So I'm saying I have to meet all those criteria to the right of this line, to the left of this line, below this line, and above this line. So it looks like my true area is in here. And I can test a point. I can take my 0 point here as a test situation. And if I say for the first equation, 0 plus 0 less than 2, that's true, isn't it? And if I take any point here for the second equation, if I put x is 0, that's greater than -2 and less than 1. So that's true for that second equation. And putting in a 0 here, 0 is greater than -1. That's true. So this point here, this test point, if I say my test point is 0, 0, x is 0, y is 0, and plug it in, it satisfies all the above equations. So I can say then that, well, my solution area is the area shown here in yellow. It's this area here. And it includes the points along this vertical line, does not include the points on the horizontal line or the vertical line or the slant line. Okay, so, and this is my test point here. Okay, so the solution, if you're asked to graph this, you graphed the 3 lines. It turned out to be 4 lines because this is an x less than 1 greater than -2, which gave me 2 vertical lines. Okay, so I got these 2 verticals and this y and this y. Okay, can you see that okay? And then my solution area there is shown in here. And my test point was at 0 and 0. Okay, questions on anything we've covered? I think I'm going to stop at this point. I think I've covered what I need to cover. These shapes can be different kind of shapes, but you're always looking to plot those shapes, determine whether the shape line is included or not included. That is to say, is it greater than or less than or equal, or just greater than or less than, and then put in a test point. Okay. Questions on anything we've covered? I think I'm going to stop at that point and call it a day for section 7.5.
I have a quick question.
Yes, go right ahead.
So since we've tested the point at 0, 0, and we found that it's true, does that automatically mean that every other section is false?
You could put it in and test, but yes, the answer is yes. You could test multiple points within this area. You could pick any point you wanted to in this area. 0, 0 happens to be an easy one to test.
Mhm.
And you could pick any point outside. You could pick 5 and 0 and do a test. Okay, and if you did that for the equation x plus y less than 2 for 5 and 0, that says 5 is less than 2, and that's false, isn't it? Which says this area out here is false. But you can pick any point you want out here and put them in the equations. And you'll be able to satisfy yourself that anything outside this area right here is false. All these areas out here are false. We can put in a -4 and a 0, -4 and a 0. And we're going to say, well, that's false. You know, it just depends on if we, in other words, we have to be, if we pick just this line, x plus y less than 2, or y equals -x plus 2, that's this line here. Well, it's true for this line. But we can't be just true for one line. We have to be true for all the lines. We have to be true for this line, and these two lines. And so if I pick a point out here at -4 and 0 and say, well, gee, it worked in the first one. Well, that's true. It worked for that line. That's true. But it doesn't, it's not inside the box. So it doesn't work for this set of lines, and it doesn't work for that line there.
Okay, cool. Thank you.
Sure. So I think the easiest way is to pick a point inside whatever shape you've determined to be true and test it. Now you could test multiple points if you wanted to, but you don't need to. Anything inside here will test to be true. And that's included that, not included, not included, not included. All right. If there are no other questions, when am I going to see you next?
See you on Monday, Professor.
Monday. And what are we going to do on Monday?
8.1, 8.2, I believe.
Now let's take a look here. Monday, we've completed that. So yes, we'll do 8.1 and 8.2 on Monday. And then I don't have anything particularly scheduled for the Wednesday. I'm going to leave that open for any kind of questions you might have on anything we've covered. We'll just leave that an open session. And then we'll have our final on the 15th during class hours. Okay. Any other questions before we go for the weekend?
So how many questions will the final will be?
I don't know. It's generally, because it's 2 hours, it's probably going to be more than 20. Probably, generally we've been having 10 questions. It's probably 20 to 30 questions, I'm going to guess, because generally what happens on the final, and I haven't taken a look at exactly all the questions, but you'll have parts, you'll have part A, B, and C, solve for this, that, and the other thing. So you'll have enough time to get through it, I think.
Okay, thank you.
Sure. Okay, everyone, have a great weekend.
Thank you. Have a good day.
Thank you, Professor. Bye.